Okay, kiddies, we are doing another science video, and today we're actually going to be doing some real physics. And we're going to be talking about Newton's laws. Let me just write that out. Newton's laws. There we go, it's right there. Okay, so this video is not going to be very mathy, but I don't care. You're going to deal with it. I know how heartbroken you are to hear that, but oh well. So the first thing that we're going to talk about is Newton's first law, which makes sense because it's his first law. So first law. What is the first law? It's sometimes referred to as the law of inertia. Law of inertia. Right? And it is basically the tendency of things with mass. It's the tendency of mass to want to continue moving. So basically what it's saying, well, that's what inertia is. Inertia is the tendency of mass to continue moving. So basically what it says is that if you have an object, a magical flying block, and it's flying through space, with a certain velocity. It's flying through space with a certain velocity. Then it will continue flying through space with that constant velocity unless there is a force acting upon it. So how can we write that out? We're going to write that out as let's just say that the velocity does not change. No, I'm going to write this out really short. No change in velocity unless force is present. Okay, so if there's no force, there's no change in velocity. And what's change in velocity? It's acceleration, okay? So we can write that down as change in velocity equals acceleration, which is equal to the time derivative of velocity. For those of you who have done calculus and know what a derivative is, then there's that for you. The time derivative. Can't see it too well. If I only had somewhere to hold this up, I could probably maybe push this back a little bit like that. See, that works! Look at this! This is awesome. Okay, so we have the law of inertia. So now so what's the second law? Because it's basically summarized as the first law. These are very simple, very simplistic laws. The second law, or we're going to write a number 2 here. The second law is that basically it can be expressed in an equation. F equals ma. Okay? And so the first law describes how mass doesn't want to. So we basically concluded that because there is no acceleration, which is change in velocity, there is no acceleration unless a force is present, which is shown here. This is the actual relation, where F is equal to the force. Let me write that out. F is the force, right? M is the mass of the object, and then A is acceleration. Acceleration. God, that's blurry. I wish I had some way to fix that, but I don't. I guess I can move it up a little bit. So yeah, A is acceleration, F equals ma. Okay, that's the second law, pretty much. Okay, so the third law, which is right here, is going to be the famous, for every action there is an equal and opposite reaction. I don't want to write that out. So what that means basically is that if we have like two people pushing on each other, they're pushing, right? And the force between them is going to act simultaneously on both of them. The force isn't going to be directed toward either one of them. It's going to be simultaneously acting on both of them. And so what that means is, and that also implies that force arises from interaction with, interaction with matter, okay? So, what else do I need to do? Okay, that's it for Newton's laws. And now I'm going to go into, the derivatives, because I mentioned here that acceleration is the time derivative of velocity, and I'm going to go into that for those calculus people right now. Okay, so now we're going to do the time derivatives of position. Okay, so we're going to start with position, which is represented by x. Okay, that's position. Okay, and one way to, and this is equal to, well, that's just x, okay? And we're going to write that down. This is position. Okay, there's position. Okay, and let's observe what happens when position changes over time. What is that called? Like when an object would move from here into here. What's change in position? Or here's a kinematic equation that some of you may know. So we have the position final minus the position initial divided by time. What is that? Oh, that's just speed. Look at that. Speed, or velocity, okay? And we're going to use velocity, because velocity is a vector and it's a lot more descriptive. Okay, so that's just velocity, right? So we can write that down as the change in x is equal to velocity, right? And did we already say that? No, we didn't. Okay, so change in velocity, and this also means that if we take the derivative of x with respect to time, or derivative, or this is the partial derivative, but whatever, this is velocity, okay? So that's the first one, and then now we have velocity, okay? What happens if we have change in velocity? Well, we already went over this. A change in velocity, if the velocity is changing, then we get acceleration, which is equal to a, which is equal to this t, but this is also equal to the second derivative of x with respect to time. Look at that. You can do that. That's perfectly cool. And so that's something. And I guess we could go. Well, I'll go one step further and say that you never really need this knowledge, but I'll tell you anyway. The change in acceleration is equal to jolt. Okay, and which is equal to the derivative of acceleration with respect to time, which is equal to the second derivative of velocity with respect to time. Let's write that out. And then that's equal to the third derivative of position with respect to time. Okay, and there's something, and that's pretty much all you need to know, but I'll continue, because there's a little bit of notation you still need to know. Okay, so if you have the time derivative, if you have the first time, so there's a shorthand for this, so you don't have to write. Because we might want to use VAJ, whatever, for different symbols in physics. So there's a shorthand for these, and it's just, you just put, like, if you have x, we already concluded that just x is the position. But if you put a dot on top of the x, just called x dot, that's the velocity, and that stands for one time derivative of position. Okay? And if you want to write acceleration, this is 2x dots. Okay? And if you want to do jolt, and this is rarely done, but I'll do it anyway, it's just so you get it's 3 dots. Okay? So, yep, that's just a little bit of notation. You need this. So, like, for example, we learned today that F equals ma. Especially in analytical mechanics, you would see this rewritten as F equals mx dot dot. And that just makes it easier to take derivatives of that, because if you want to take time derivatives of this, you just remove or add a dot. Okay? Or if you take antiderivatives, you remove the dot, and if you take derivatives, you add another dot. Okay? That's just a little bit of notation for you guys. My name is Yuichi Garrett from Solitaire Spade, and I am signing off now.